This is lecture 4F, the final lecture of the semester. In fact, the final lecture of general chemistry, which is kind of sad, but it had to come at some time no matter what. So here we go. We're going to talk today about reaction mechanisms. Chemical reactions occur in a specific series of collisions. If you think back to the basic theory that explains kinetics, that is collision theory, molecules must collide to react. So any chemical reaction that occurs happens by a series of collisions, and each collision is considered a step. So a reaction mechanism describes the steps that are needed for a chemical reaction to convert its reactants into products. Now, each step in a mechanism has something called a molecularity. That's just how many molecules are colliding in that particular step. So for example, if just one molecule decomposes because maybe it slaps itself into the side of the container, we call that a unimolecular step. But if two molecules have to collide with each other, two reacting molecules have to collide with each other, then we call that a bimolecular step. And although it's fairly rare, if three molecules were all to collide together at once to form a chemical change and cause bonds to break, that would be called a trimolecular step. So all these collisions, all these steps that cause reactants to turn into products are what we call the reaction mechanism. It's the series of steps or the series of collisions that yield a balanced chemical reaction. Now, occasionally, a chemical reaction will occur in just one collision. That's the most elementary type of chemical reaction there is, so those are called elementary reactions, a reaction that occurs in only one step or in one collision. But most chemical reactions occur in a series of collisions or a series of steps. And if we want to relate the reaction mechanism to the rate of a chemical reaction, then what's important is going to be the step or the collision in the mechanism that takes the longest time, the slowest step. So for multiple step reactions, if we want to try to predict how fast the reaction is going to go, we want to focus in on the slowest step. That's called the rate determining step or the rate limiting step. It's the slowest step in the reaction mechanism. Why is it the one that determines the rate? Here's an example. Let's say you're here at Saddleback College and you're going to head to Corona. If you want to go from Mission Viejo to Corona, it's essentially a three-step process. You're going to have to drive on the 5 freeway. Then if you want to use the toll road, you can go on the 241, and then you're going to go on the 91. So a three-step pathway to get from Mission Viejo to Corona. Now in the afternoon, 5 freeway is not too bad as long as you don't get into Irvine, so you can go maybe 65 miles an hour. And the 241, certainly you can go 65 miles an hour. Hardly anybody's ever on the toll roads, right? But if you get to the 91, I've ever been on the 91 in the afternoon going east, oh my goodness. The average speed of the 91 freeway going east is about 5 miles per hour. And really, doesn't matter what your average speed is on the 5, 65, 75. Doesn't matter what your average speed is on the 241, 65, 75, 85. The amount of time it's going to take you to get from Mission Viejo to Corona is completely dependent upon what's happening on the 91. And if you're going 5 miles an hour on the 91, doesn't matter if you were racing really quickly on the 5 and the 241, you're stuck. The 91 freeway is the rate determining step to drive to Corona. So in chemical reactions, same concept, we're going to focus in on the slowest step. So it turns out that if you want to predict what the rate law for a chemical reaction is, if you know its mechanism, you go to the slowest step. And the order of each reactant in a reaction's rate law will come from the coefficients of the reactants in the rate determining step. So if we have a reaction like this and we want to determine the rate law, and the rate law is going to be rate equals K multiplied by the concentration of NO to some unknown power X, multiplied by the concentration of H2 raised to some unknown power, we'll call that Y. We can experimentally determine what X and Y are, but if you actually know the mechanism of this, you don't have to do experimental work. You can predict what the rate law is directly from the mechanism. So this reaction, it's been studied, it actually occurs via a three-step mechanism. There's an equilibrium in which two nitrogen monoxide molecules combine to form an N2O2 molecule. Then the N2O2 molecule will collide with a hydrogen molecule to form N2O and water. And then the N2O molecule will collide with another hydrogen to form N2 and H2O. And if you add these up, this adds up to the overall reaction at the top of the slide. In this mechanism, and this is actually a hard thing to determine because collisions happen so quickly, it's on such a microscopic scale that chemists that study kinetics, long, arduous process. So it's actually hard to get a mechanism, but if you do have one, if you know which is the slowest step in the mechanism, that's the only one that determines the speed of the reaction. And in the slowest step, our reactants are N2O2 and H2, and they both have coefficients of 1. That means the rate law is going to be rate equals K multiplied by the concentration of N2O2 to the first multiplied by the concentration of H2 to the first. So if you know the rate law, you can directly, if you know the mechanism, you can directly get the rate law. Now, if that makes sense, when you write a rate law, you always want to have the rate law showing rate is proportional to a constant, which is related to temperature, multiplied by the concentrations of the reacting molecules raised to some coefficients as powers, or raised to some powers. And in this case, one of the substances in our rate law is N2O2. That is not one of the reactants in the overall reaction. In fact, it's not even a product. What it is, it's called a reaction intermediate. So this is not a reactant in the reaction. It's something that gets produced at the end of step 1, but gets reacted away at the beginning of step 2. So it's called an intermediate, a reaction intermediate. And you never want to have your rate law have as one of the substances in there a reaction intermediate. You almost always want to have the rate law be proportional to the concentrations of the reacting molecules. Occasionally a product molecule will wind up in there, but never a reaction intermediate. So that means the N2O2 needs to be substituted out. So for us to get a proper rate law, we've got to get rid of that N2O2, and here's how we're going to do it. If you go to the 3-step mechanism, and if one of the steps is in equilibrium, that's going to be the key. In this case, only the first step is in equilibrium. I'm going to write the equilibrium constant expression for that first step. If you notice above the double-headed arrows in step 1, there's a capital K. That stands for the equilibrium constant for step 1. What do I have above the yield signs in steps 2 and 3? Those are lowercase k's. Lowercase k's stand for specific rate constants. So when you have an equilibrium, you'll be given an equilibrium constant as a capital K. And when you're given a non-equilibrium reaction, you'll be given just the specific rate constant, which is a lowercase k. So for that first reaction, that first step, which is a fast equilibrium, I can say the concentration of N2O2 divided by the concentration of NO squared equals the equilibrium constant K1. This will be the equilibrium constant expression for that first step. It has the reaction intermediate in it, the N2O2. So I'm going to solve this for N2O2. And N2O2 will equal K1 multiplied by NO quantity squared. Well, now I can substitute the N2O2 out of the rate law and replace it with K1 multiplied by NO squared. I've kept the yellow color there so you can see what I've done. Now I have a rate law that's only in terms of the reactants. It's in terms of NO and it's in terms of H2. Now, a rate law always has a specific rate constant that's proportional to temperature. What we've done here is we've determined the actual specific rate constant is actually the product of the specific rate constant for step 2 and the equilibrium constant for step 1. I'm just going to multiply the K2 and the K1 together, and I'm going to call it K for this overall reaction. So our rate law is going to equal K times the concentration of NO squared times the concentration of H2. If I asked you what's the order of this reaction, you would say it's second order in NO, first order in hydrogen, third order overall. If I ask you what is the molecularity of each step in the mechanism, remember what that means. That's the number of molecules that are colliding in the particular step. So in step 1, we have 2 NO molecules that are colliding. Its molecularity is 2. The second step, we have an N2O2 colliding with an H2. That's 2 molecules. Molecularity is 2. In the third step, molecularity is 2 as well. An N2O is colliding with an H2. So in this particular mechanism, we could describe the molecularity of each step. And when you get the rate law, then you can explain the orders of each of the reactants and the overall order. Let's try this process again. The reaction of CHCl3 with Cl2 forms CCl4 plus HCl, and we've determined experimentally that this reaction has a three-step mechanism. First step is a fast equilibrium where chlorine molecules are decomposing into chlorine atoms. Second step is CHCl3 reacts with a chlorine atom to form CCl3 plus HCl. And the final step is CCl3 plus Cl forms CCl4. If you're given the mechanism, no experimental data is needed, you can go directly to the mechanism, find the slowest step, and see what the reactants are in the slowest step. It's CHCl3 and Cl. They each have coefficients of 1. That means the rate law will be rate equals K multiplied by the concentration of CHCl3 to the first multiplied by the concentration of Cl to the first. That's your rate law, and the specific rate constant was K2 because it's the second step. Now, are these two substances in our rate law reactants in the overall reaction? The CHCl3 is, but the Cl is not. That's a chlorine atom, and what's in our reaction are diatomic chlorine molecules, so this Cl atom has to be substituted out. And the only way you can do that is to go to a step that's an equilibrium, which is our first step. So if I write the equilibrium constant expression for the first step, K1 will equal concentration of Cl squared divided by concentration of Cl2. I want to substitute out the chlorine atoms, so I'm going to solve this for chlorine atoms by moving the Cl2 molecule over to the left side, and then I would actually have to take the square root of both sides. So the right side becomes just the concentration of Cl, the left side becomes the square root of K1 and the square root of Cl2, and the fancy way to write square roots is to raise them to the 1/2 power. So I'm going to take the left side of this equation and substitute it into the rate law where our atomic chlorine is located. And so the rate law becomes K2 multiplied by the concentration of CHCl3 multiplied by K1 to the 1/2 power multiplied by Cl2 to the 1/2 power. The two K values can be merged together to make the overall specific rate constant for this reaction. And so our rate law would be K equals concentration of CHCl3 multiplied by concentration of Cl2 to the 1/2. What's the order with respect to each reactant? It's first order with respect to CHCl3. It's 1/2 order with respect to chlorine, and it's 1.5 order overall. What would be the molecularity of each of the steps? Our first step only has one molecule reacting. It has a molecularity of 1. Our second step has 2 reactants reacting. Molecularity is 2. And the third step has 2 reactants reacting. Its molecularity is 2 as well. Let's try one more example, maybe just a little bit more challenging. For the reaction hydrogen and iodine forming hydrogen iodide, this reaction also occurs via a 3-step mechanism. First one is a fast equilibrium where the diatomic iodine breaks down into iodine atoms. The second step is a hydrogen molecule reacting with an iodine atom to form H2I. And the third step is the H2I reacting with an I to form 2 HIs. To predict the rate law for this reaction, we focused in on the slowest step in the mechanism. And so the rate law will say rate will equal constant multiplied by the concentration of each reactant to their coefficient as a power. That would be the concentration of H2I to the first, multiplied by the concentration of I to the first. This is our rate law, the K3, because the constant came from the third step. Now, both of these substances, H2I and I, do not appear in the overall reaction at the top of the slide. We have to substitute them out, so let's do it one at a time. You can only substitute things out with fast equilibria, and if you want to substitute out the H2I, you've got to find an equilibrium that has H2I in it. So I'm not going to use the first equilibrium, I'm going to use the second one. This is the one that has H2I in it. So if I write the equilibrium constant expression, K2 will equal the concentration of H2I divided by the concentration of H2 multiplied by the concentration of I. And to solve for H2I, I'm going to move all the denominator over to the left side. So the molarity of H2I will equal K2 times the molarity of diatomic hydrogen times the molarity of monatomic iodine. And if I substitute those in place of the H2I in my rate law, I have this new expression, rate equals K3, K2, concentration of diatomic hydrogen, which is good. That's a reactant in the overall reaction, then multiply by the concentration of atomic iodine, multiplied again by the concentration of atomic iodine. And the problem here is these do not appear in the overall reaction. Those are monatomic or atomic iodines. We need to substitute them out to make diatomic iodine. So to substitute those out, I'm going to have to use the equilibrium that has monatomic iodine in it, and that's the first one. This equilibrium, constant expression, will be K1 equals concentration of I squared divided by the concentration of I2. And if I solve this for the concentration of the I squared, I just bring the concentration of I2 over to the left side. I'm going to make my substitution right now because in my given rate law at the bottom left, I have I times I, which is concentration of I squared. And so that's just going to equal K1 times the concentration of I2. So the final rate law now will have hydrogen, diatomic hydrogen to the first power, diatomic iodine to the first power. They're both reactants in the overall reaction. And I'm just going to multiply K3 times K2 times K1 to make the overall specific rate constant K for this reaction. So the rate law is going to be K equals concentration of hydrogen times concentration of iodine. First order with respect to hydrogen, first order with respect to iodine, second order overall, and the three different steps, their molecularities are respectively 1, 2, and 2. So that's what we can do with a reaction mechanism. Now, what determines how fast or how slow a reaction is going? Well, collision theory, molecules must collide to react. They must collide with a sufficient amount of energy. They must collide in the proper orientation. And here at the end, we're going to focus in on that amount of energy you need for a chemical reaction to occur. There's a name for that. It's called the activation energy, E sub A for energy of activation. It's the minimum energy needed by the reacting molecules to have an effective collision, to cause bonds to be broken and new bonds to be formed. So if we draw an energy diagram for a chemical reaction that converts reactants into products, we have an energy content of the reactants at the left and energy content of the products at the right. The difference between those two is how much energy is given off or absorbed in the reaction. We have a name for that. That's called the enthalpy change. So graphically, if you just figure out the difference in the reactant and product energy levels and subtract them, actually products minus reactants, you'll get the enthalpy change for the reaction. Now, what's that hump indicate in the middle of this? Well, that's indicating how much energy you have to add to the reactants so that the reactants can go over the hump and turn into products. Graphically, this is what the activation energy is. You show how much energy you must add to the reactants to allow them to be able to be converted into products. Now, let's relate activation energy and collision theory. So collision theory talks about microscopic levels for chemical reactions, and the speed of a chemical reaction depends upon the three steps in the collision theory. First, molecules have to collide. So how often are they colliding? The more often they collide, the faster the reaction rate's going to go. Now, some fraction of the collisions are going to have the proper orientation. This pretty much doesn't change. It's just a statistical thing. There's 2%, 8%, whatever it is, of the collisions will have the molecules in the right orientation so they will react. But the third thing that's important is the fraction of the collisions that have the required energy, or as we would say, have the activation energy. If I graph the kinetic energy of a bunch of molecules in a sample, and so the number of molecules is on the y-axis and their kinetic energy is on the x-axis. If you're at a certain temperature, molecules have a certain average kinetic energy, but it doesn't mean every single molecule has the same amount of energy. Some have low energy, some have high energies, and as they collide with each other, much like how pool balls collide with each other on a pool table, energy gets transferred. So they're always having a variety of different energies, but there's a definite average there. So there's a big distribution of kinetic energies of any molecules in a sample. The activation energy is the minimum amount of energy needed to make a collision effective. So we can graph that somewhere on the x-axis. Where might the activation energy be? Maybe it's here. So out of all the molecules in a sample here, what fraction of them, when they collide, will have enough energy for a successful collision? Oh my goodness, it's like 1%. It's really, really small amount. So if you have a relatively high activation energy, you're going to have a really small number of collisions that are effective. And our energy profile might show that there's a really large activation energy for this reaction because the activation energy is so high. But what if we had a reaction where the activation energy was here? You would have a lot more molecules that would have a sufficient energy to collide. The reaction would go a lot faster. How would I graph that on the right side here? With a lower activation energy, I bring that hump down like this, and the lower activation energy tells the chemist, oh, a higher percentage of the collisions are going to actually be effective. So activation energy is really important in relating to the fraction of collisions that have the required activation energy. Now, in lab, on the macroscopic level, the rate of the reaction depends upon two things we can measure. First is the concentration of the reactants. So if you put more reactant molecules in a container, there's going to be a better chance of them colliding, so the reaction is going to go faster. If you don't put very many reactants in a container, they're not going to collide very often because they are in empty space most of the time, so the reaction will be slow. But the other thing that affects the rate of the reaction is temperature. If you raise the temperature, reactions go faster. Why would that be? If we have a sample of molecules at a particular temperature, I'll call it T1, and there's a distribution of kinetic energies at any given temperature, and for some reaction that has a specific activation energy, maybe this is the activation energy, at T1, only this 1% of the molecules will have enough energy to cause an effective collision. But what if we change the temperature from T1 to T2, where T2 is a higher temperature? What does this curve do when the temperature gets higher? The average kinetic energy moves up, so the whole curve shifts to the right. So at a higher temperature, the distribution of kinetic energies of the molecules looks like this. What fraction of the molecules now have the necessary activation energy to react? Wow, like 33%. So temperature has a major effect on speeds of reactions or rates of reactions mostly because when you raise the temperature, you increase the fraction of the molecules that have the required activation energy. That makes more of the collisions successful, and if you have a higher percentage of the collisions being successful, the reaction goes much faster. Now, I would like you to be able to draw and read reaction energy profiles like we've been showing you before. So on this graph, if you measure the distance or difference between the reactant level and the product level, and you go products minus reactants, you're calculating the enthalpy change of the reaction, how much heat energy is given off or absorbed. If you measure the difference from the reactant level to the highest point in the curve, you're measuring the amount of energy that you have to add to the reactants to cause a successful collision. That's the activation energy. So this would be a graph of a chemical reaction where you can physically measure delta H and E sub A. This particular reaction we've shown here is exothermic because the products have a lower energy state than the reactants. The reactants react and overall they give off energy because the products now have a lower level. What would be true about delta H if you have an exothermic reaction? It should be negative, because how you would calculate delta H is you would go final minus initial, energy level of the products minus energy level of the reactants, and because the products are lower and the reactants are higher, you'd get a negative number. So for this, delta H would wind up being a negative value. Activation energies are always positive, no need to worry about them changing sign. If we have an energy profile that looks like this, the delta H of the reaction is still the difference in energy states between the reactants and products. And the activation energy is still the energy you have to add to the reactants to get to the highest point on the curve. So you can see the activation energy is really high for this one. Because the product energy level is higher than the reactants, this is an example of an endothermic reaction. So this reaction, the reactants have to absorb energy to become the higher energy products. So delta H would be positive. And mathematically, if you go final minus initial, the energy state of the products, which is a high number, minus the energy state of the reactants, which is a low number, would have to give you a positive value. So for any reaction profile, I would like you to know that this distance right here is going to be your enthalpy change, but you'll need to understand that this case would be a negative value. If the reactants and products were reversed in energy, it would have been a positive value. The level between the reactants and the highest point in the curve is the activation energy specifically for the forward reaction. And the reason I'm saying that specifically is, what if you want to talk about the reverse reaction? Well, the green line is still the delta H for the reverse reaction, only now it's positive instead of negative. But the activation energy for the reverse reaction would have to be how much energy you have to add to the products to get over the energy barrier, which would be this blue line. So we have from an energy profile, the enthalpy change for either the forward or reverse reaction, which is the same value, the green arrow, but positive or negative, depending upon the direction you're going. The red arrow, the activation energy for the forward reaction, and the blue is the activation energy for the reverse reaction. They're related to each other. If you take the activation energy of the forward reaction, which is red, subtract the activation energy of the reverse reaction, which is blue, you actually get the delta H for the reaction. Now, when a reaction occurs, at the highest point on this graph is where the reactants are going through a high energy state that's called the transition state. So the left side of the reactants, the right side of the products, what's at the top of that curve there? That's called a transition state. It's like when you're driving to Bakersfield or something, you have to go over the Grapevine, which is the mountainous pass that separates Los Angeles County from Central California. So this is going over a pass that's called a transition state. And at the transition state, this is where the reacting molecules are colliding, and for a brief instance, they form a single unit that's called the activated complex. Now, that little symbol we use for the activated complex actually comes from footnotes in textbooks and literary works. If you have a book and there's a footnote on the page, quite often they'll put the first symbol here I've shown for you, which is called a dagger, and down at the bottom there'll be a dagger. It'll say what the footnote is. If there's a second footnote on a page, they use the other picture, which is called a double dagger, and for whatever reason, the double dagger has become the symbol for the activated complex. So sometimes you'll see that symbol written at the very top of your energy profile. That indicates the complex that's created where the reacting molecules have collided with each other, and for one brief instant, they're all stuck together. So if you have an iodine molecule and a hydrogen molecule, and they're going to collide to turn into two HIs, the instant they collide and they're stuck together just for that one instant, this is called the activated complex. The original bonds between the two green iodines are starting to break. The original bonds between the two red hydrogens are starting to break, and you're starting to form bonds between the H's and the I's. So this is the activated complex, a single unit in which old bonds are breaking and new bonds are forming. Now, one other thing that can affect the speed of a reaction is a catalyst. I want to talk about catalysis a little bit. A catalyst increases the rate of a reaction, and the way it does it is it allows the reaction to take place via a different pathway that has a lower activation energy. Let me explain what I mean. If you go to McDonald's and you get a drink, they've got those cute straws at McDonald's with the red and white stripes on them. Have you ever taken one of those straws and flicked it with your finger and it goes pop? Well, if you take the straw in this drink right here and you try to flick it to make it pop, not going to happen. The energy you would have to use to flick that straw is really, really high. So to pop that straw, you need a really high activation energy. But there's another way to get that straw to pop. Have you done this before? You take the straw and you wrap it around your fingers. And when you wrap it really, really tightly, then you come up with your other finger and you just go pink like that and pop. It pops really loud. What have you done? You've stressed that straw such that you only needed a lighter collision to make it pop. You've changed the pathway now to have a lower activation energy. This is what a catalyst does. A catalyst bonds to a reacting molecule, like maybe an iodine I2 molecule. It bends the molecule, stretches that bond, so that bond is just about to break. So if something soft comes up and goes pink and just touches it, it pops and reacts away. So a catalyst strains the bonds in a reactant or in the reactants such that a weaker collision can cause the reaction to occur. Now, a catalyst makes the reaction go faster because more collisions will be effective now. It allows a reaction to come to equilibrium faster, but it never changes the equilibrium concentrations. So it just helps you get there more quickly, but you can't actually use a catalyst to make more products in a chemical reaction. One very common catalyst is a metal surface. It's a catalyst for gaseous reactions. If you have the reaction between nitrogen and hydrogen, to do this, you've got to break the triple bond in the N2 molecule, And you've got to break the single bonds in the H2 molecules. It takes a lot of energy to do that. There's a high activation energy for this reaction. But if you put nitrogen and hydrogen molecules into a container that has a bunch of palladium or platinum metal in it, those diatomic molecules come down with London dispersion forces, get attracted to the metal atoms, and then the neighboring atom attracts the other end of the molecule, and it actually pulls the molecule apart. Can you see the two little black dots there on the 4th and 5th palladium atoms there? The H2 molecule has been broken apart, and just below them to the left, one of the nitrogen molecules has been broken apart. So attractive forces in the metal break the diatomic molecules up into individual atoms, so all they have to do now is recombine to form the products, and the reactions occurred via a different pathway that has a lot lower activation energy. That's how catalysts work. Now, in 1889, really close to the time that SVANTE ARRHENIUS had proposed definitions of acids and bases, he was studying chemical kinetics. And he proposed a mathematical explanation for what the specific rate constant is in a chemical rate law. He proposed that the specific rate constant K is actually the product of the collision frequency, the fraction of the collisions with proper orientation, and the fraction of collisions with the activation energy, the three steps in our collision theory. So he said all of those contribute to what the value is for the specific rate constant K. The collision frequency we call Z, that could be like 6 million molecules colliding per second, some huge number. P is the fraction of collisions with the proper orientation, so that's going to be a fraction like 1/3, 1/4, so like 0.23, 0.14, whatever it is. And then a final term that he determined mathematically, e to the negative e sub a over RT, is the fraction of the collisions that have the activation energy. What does that mean? Remember our energy profile from before? If you have an activation energy, what fraction of the molecules will have enough energy in order to react? They're the red ones in that picture there. So that picture, that 33% or whatever it is, that 0.33 is what he's calculated here in his third term. So he proposed that a specific rate constant equals Z times P times e to the negative e sub a over RT, where people don't really care too much about the Z and the P, so we just multiply them together and call them A, which we call the pre-exponential factor. So essentially, what Arrhenius has done is he's related the specific rate constant of a rate law to, look in the exponent, the activation energy of a chemical reaction. So A is the pre-exponential factor, but E sub A is something that you can now theoretically or experimentally calculate. It's the Arrhenius activation energy, and it can be determined if you know the value of K from a rate law. So the activation energy can be determined graphically if you know the specific rate constants at different temperatures. Now, how do we do that? If this is the equation that Arrhenius said the specific rate constant equals, it's the pre-exponential factor times e to the negative e sub a over RT, I'm going to take the natural log of this entire equation. If I do, I'll get natural log of K equals natural log of A minus E sub A over RT. If I switch those two terms around on the right side, I have natural log of K equals negative E sub A over RT plus natural log of A. Can you see y equals mx plus b in there? Look carefully. What's the y? That would be natural log of K. What's x? Has to be a variable. What's the variable in there? Let me write it a little bit differently. It's 1 over t. So if you plot on the y-axis the natural log of a specific rate constant that you can determine experimentally, and then the slope will be negative e sub a over r, you'll plot on the x-axis the reciprocal of the temperature, and then the intercept will be the natural log of the pre-exponential factor A. You can actually use this to calculate activation energy. This is what we'll do in experiment 26. You're going to measure the specific rate constant for a chemical reaction at 3 different temperatures, and then you're going to make a graph of the 3 different specific rate constants, their natural logs, at the 3 different temperatures. And if you do that on Excel, I've got my column here for my x values, my 1 over t's, that's the reciprocal of 3 different temperatures. And then here's the natural log of the specific rate constant at those 3 different temperatures. And if you graph that, Excel is going to show you what the equation of the line is, and all I care about is the slope. What is that? Negative 3,413.5. What's significant about that? Well, the slope equals negative E sub A over R. So if I want to solve for E sub A, I'm going to bring the negative sign in the R over to the right side. My activation energy will equal negative R multiplied by whatever the slope is on my Excel graph. So R, in terms of energy units, is 8.314 joules per Kelvin. My slope, negative 3,413.5, and the units have to be Kelvin because I'm graphing natural log of K versus 1 over T. Natural log of K has no units. 1 over T is reciprocal Kelvin. So 1 over reciprocal kelvins is kelvins. They cancel out. The answer comes out in joules, and we've determined the activation energy of this reaction, 28,400. So we've now covered all the material you're going to need to know for test 4. Let's go through some of the terms you want to make sure you're clear on before our exam. You should know what a coordination complex is. It contains things bonded to a central metal. Those are called ligands. Those ligands can be monodentate or polydentate. Polydentate ligands are sometimes called chelates. The type of bonding that a ligand undergoes when it bonds to a central metal atom is called a coordinate covalent bond. You should know what that is. And the number of bonds that ligands are making to the central metal constitute the metal's coordination number. We spent a good deal of time talking about nomenclature, so you need to be able to write me the names or formulas of coordination complexes. And then we talked about isomers, and I'm going to ask you to try to identify how many structural isomers there are for a formula, how many geometrical isomers there are for a formula, and how many optical isomers there are for a formula. In terms of equilibrium, we found that when you form a coordination complex, you get an equilibrium existing between the metal and the ligands in the complex, and the equilibrium constant for the formation of that complex ion is called a formation constant. I'll expect you to be able to do calculations based upon that formation constant, just like other equilibrium constants we've done earlier in the semester. We talked about crystal field theory, and so I want you to know the d orbital splitting for crystal fields that are octahedral, square planar, tetrahedral, and linear. This will then determine how the electrons are spread out into the d orbitals. If you have a couple of different possible arrangements for d orbitals, d electrons, they can either be high spin or low spin, so know what those are. You should be able to predict whether something is paramagnetic or diamagnetic. And then I want you to know what ligands cause weak fields and what ligands cause strong fields, and be able to explain to me why certain things like chloride ions are weak field ligands, but things like cyanide ions are strong field ligands. We actually calculated what the splitting energy was in an octahedral field based upon electromagnetic radiation equations. I'd like you to be able to do that. And then we finally defined what Lewis acids and Lewis bases were, the most comprehensive definitions of acids and bases, because when a complex ion is formed, the reaction between a ligand and the central metal is actually an example of a Lewis acid-base reaction. Our last chapter was on kinetics. You should definitely understand collision theory. And we talked about how you measure the rate of the reaction, either by the disappearance of a reactant or the formation of a product. And if you write an algebraic relationship showing how the concentrations of the reactants affect the rate of the reaction, we call that a rate law. The constant in the rate law is called the specific rate constant, and the exponent to which each reactant is raised to is called its order. I would like you to be able to calculate rate laws from concentration and initial rate data. That was homework 4D. I would like you to know the algebraic equations and linear plots for zero order, first order, and second order, and then be able to determine a rate law from concentrations in time, which was homework 4E. Then today we talked about reaction mechanisms. You should now be able to determine a rate law theoretically from the reaction mechanism. We learned about what the activation energy was. I'll expect you to be able to read an energy profile, know what the transition state is, what an activated complex is, and then you should know how a catalyst affects the rate of the reaction, what it actually does to make reactions go faster. We finished by talking about how to calculate the ARRHENIUS activation energy, and you'll be doing a calculation like that in experiment 26 and definitely on the homework, and you'll do that on the test as well. The experiments that I'd like you to know in preparation for this test are 20 to 26, and of course you've read your 2 chapters.